Hypothalamus Artificial Intelligence, HI. Digital transformation powered by autonomous and intelligent algorithms in real time. Presents the conference. High Power 6.0. The artificial brain of electricity and gas sector companies. Digital industrial revolutions. Today, the evolution of industrial revolutions is conceived as Industry 6.0 has arrived. Are you ready? Industry 6.0 is completely changing the mathematical modeling of artificial intelligence. Now we can talk about orchestration of swarms of cognitive robots, and living industrial ecosystems. These two terms are new to most people, including scientists, even though they date back at least 15 years. Industry 4.0 is a consequence of the invention of the digital computer and digital automation. Its origin may be in 2000, and the result is digitalization and interconnectivity, smart factories, that is, cyber-physical systems. From a math perspective, digital revolutions don't affect math itself, but how it's used, technologies. Industry 5.0, the first mentions date back to 2015, is humanization and close collaboration between people and cyber-physical cognitive robots based on artificial intelligence. The transition from Industry 4.0 to Industry 5.0 represents a paradigm shift. We move from an approach focused exclusively on technological efficiency to one that prioritizes human value, sustainability, and resilience. While Industry 4.0 sought to interconnect machines so that they could make autonomous decisions, Industry 5.0 seeks to make these machines work with people to enhance their creativity and well-being. Formally introduced by the European Commission in 2021, this revolution does not replace the previous one, but complements it under three fundamental concepts. Human centrism: technology should serve people, not the other way around. It focuses on improving the health, safety, and job satisfaction of workers. Sustainability prioritizes circular processes that reuse resources, reduce environmental impact, and respect the planet's limits. And resilience, the industry's ability to withstand and adapt quickly to global crises, such as pandemics or supply chain disruptions. Industry 6.0 currently has no date, as it is considered a visionary and conceptual phase that is still being defined, but which is based on intensive artificial intelligence. Total autonomy, biological symbiosis and industrial systems that function as living organisms. There are already examples of this situation, as is the case with smart grids and the Internet of Energy. Industry 6.0 focuses on the total symbiosis between humans, machines and biological systems to create living, regenerative and deeply ethical industrial ecosystems. Unlike its predecessors, it does not seek only efficiency or collaboration, but an integration where technology self-organizes and evolves along with society. The fundamental pillars are integration of mathematics and artificial intelligence, to produce artificial general intelligence, AGI, with the ability to understand, learn and apply knowledge in any intellectual task, in the same way, or even better than a human being. Human-machine biology symbiosis, fusion of human intuition, advanced artificial intelligence, and biological systems, such as self-healing materials or neurocognitive interfaces. Cognitive and proactive autonomy, transition from predictive maintenance to self-regulation and regeneration. Systems not only detect faults but are reconfigured to avoid them altogether. Regenerative sustainability, beyond reducing environmental damage, systems are designed to actively restore and enhance ecosystems through real-time circular economies. And ethical and conscious governance, AI incorporates moral reasoning and transparency, ensuring that autonomous decisions are aligned with human values and planetary well-being. The technologies related to Industry 6.0 are mathematical modeling, translation of real-world problems into a mathematical language, such as formulas, equations, or graphs, to understand, analyze, and predict behaviors of complex systems. Generative AI and AGI, co-creation of workflows and autonomous design of products based on abstract objectives. Quantum computing, massive data processing for optimization of ultra-complex supply chains and molecular simulations. Human digital twins, HDT, Virtual replicas that simulate not only physical processes, but also emotional and cognitive dynamics of workers. Internet of Everything, I/O, and 6G, ubiquitous and ultra-low latency connectivity that enables the orchestration of swarms of cognitive robots and devices on a global and even spatial scale. Industry 6.0. A swarm of artificial intelligence algorithms, that is the orchestration of swarms of cognitive robots on a global scale. If large-scale multi-level optimization methodologies, based partitioning and decomposition of systems, are applied to get the smallest atom of a dynamic stochastic, the number of algorithms they generate could become countless. If parallel processing technologies, such as microservices, are used, the solution of a mathematical problem would be carried out by a swarm of algorithms that work autonomously and permanently to achieve the goal proposed by the decision maker. This algorithm swarm approach is currently used in artificial intelligence to manage swarms of robots, but the rules that robots follow are simple, logical and intuitive, and have no solid mathematical basis. An artificial brain can be visualized as a swarm of algorithms, cognitive robots, which have a communication structure based on a multi-level sparse matrix, and whose communication protocol is governed by mathematical laws aimed at obtaining team results. One aspect that becomes fundamental is the lives of professional people. Although professional development normally evolves to its maximum level at the end of university, however, it is common for professionals to lose knowledge during the exercise of their work and reach low levels of useful scientific knowledge. In the example, after high knowledge developed at the university, the actual exercise is limited to Excel, which is fundamentally arithmetic. This is another barrier that must be overcome. Now GPT is the intelligent, and super-fast, consultation of what is recorded on the internet, which limits many professionals to this knowledge. In 2020 there was already an awareness that the impact of industrial revolutions could be negative, and that this is apparently still happening. Digital natives are the first children with a lower IQ than their parents. This originates in the scientific gap that is forming. The difference between a scientific life and a real and ordinary life generate a big chasm, not a gap. The difference between Industry 6.0 versus and the previous digital revolutions generates a big chasm, not a gap. From Industry 4.0 we can say that the new way of mathematics is directly related to the parallel thinking, and today it can be said that like paper-based math, sequential mathematics for single-processor computers will be in the short term a dead language. As in the human brain, in the future only parallel mathematical thinking will be practical. The new analytics is autonomous, parallel, and distributed. The document. The Bender's Decomposition Algorithm, a literature review. It presents the evolution of Bender's theory up to 2016. As can be seen, the growth of parallel methods, such as Bender's partition and Lagrangean relaxation, has occurred since the Industrial Revolution 4.0. Industry 6.0 focuses on the symbiosis between humans, machines and biological systems to create living, regenerative and deeply ethical industrial ecosystems. Unlike its predecessors, it does not seek only efficiency or collaboration, but an integration where technology self-organizes and evolves along with society. Industry 6.0 is changing the mathematical modeling. Now we can talk about living industrial ecosystems, and orchestration of swarms of cognitive robots. This has led to the fact that, if desired, modeling in Industry 6.0 is autonomous, without human participation or coordination problems. High Power 6.0 is the current version of High Power, the first version of which dates to 1998. Since then, High Power has evolved to incorporate multiple problems using a multi-problem model of economic dispatch as its core. All models that integrate high power have been developed using the Optex GAMS interface. Using a Solverplex optimization studio. The integration of the models is carried out automatically by Optex, and the generated programs coordinate their communication through the database, using monolithic models, or in RAM memory using large-scale parallel optimization. All high-power models can run in deterministic, or stochastic, version with user-definable uncertainty dimensions. All models that integrate high power have been developed using the Optex GAMS interface. Using a Solverplex optimization studio. The integration of the models is carried out automatically by optex, and the generated programs coordinate their communication through the database, using monolithic models, or in RAM memory using large-scale parallel optimization. All high-power models can run in deterministic, or stochastic, version with user-definable uncertainty dimensions. Finally, it is possible to introduce new models into high power as required. It can be said that the approach presented corresponds to a version of Industry 4.0, and that the change experienced until Industry 6.0 is very large, having affected the way of implementing mathematics, which is different from having changed mathematics. However, one of the most impactful changes occurs with the arrival of the Internet of Things, IoT, typical of Industry 4.0, which began to change the models that ran at discrete frequencies, such as days, weeks, months, for real-time models, which are the ones that should be used today. Traditionally, the optimization models in the electricity sector have been individual modeling with exogenous coordination between models, based on multi-stage stochastic programming, and using large-scale optimization methodologies. The differences provided by high power are integrated holistic modeling, scientific risk modeling, multidimensional uncertainty, parallel optimization, and autonomous real-time distributed optimization. The high-end core model corresponds to the integrated representation of electricity and gas supply chains. From the basic equations, variations of the model are generated, according to the techno-economic concepts that support a specific use case. The EANG equations represent the physical dispatch of an electricity-gas system, regardless of the market in which the system is located. The main variations of the dispatch model are related to the representation of the market where the EANG system operates. The process simulates an integrated system in which the two markets, gas and electricity, are balanced according to their operating hypotheses. With respect to consumers, models tend to assume an inelastic behavior of demand with respect to price. This hypothesis can be relaxed by modeling an objective function with variable demand, where the economy's social surplus is maximized. This is for any type of electricity and gas market. For the gas system, gas, supply and transport contracts can be incorporated, since this type of commercial instrument is commonly used in the gas market, and affects its operation. The main models on the electricity market are the EED, Electricity Economic Dispatch, model optimizes the dispatch of generation infrastructure, minimizing the cost of operating the electricity system, which simulates a perfect electricity market. EED is the core model of high power, as its equations/constraints are used in multiple specific models that the agent requires to address decision support needs. From EDD, 3 models of complementary dispatch are built: Economic Perfect Dispatch, Economic Regulated Dispatch, Nash-Carnot Equilibrium Dispatch, and Unit Commitment. The first 3 models are oriented to planning and the fourth to real-time programming. Distributed Economic Dispatch. The coordination of 2 types of models are studied, economic dispatch and unit commitment. The problem will be analyzed from the point of view of Lagrangean relaxation. Lagrangean relaxation. Lagrangean relaxation is a mathematical technique used to solve complex problems of constrained optimization, simplifying them into relaxed versions that are easier to solve. It is especially effective for combinatorial optimization problems where a few hard constraints make the original problem computationally intractable. The method follows a divide-and-conquer philosophy. The steps to follow are: identify difficult constraints. Constraints are divided into 2 groups: easy constraints that can be resolved quickly, and hard constraints, lateral constraints that complicate the structure. Dualize with penalties. Hard constraints are removed from the constraint set and moved to the target function. Lagrange multipliers. Each relaxed restriction is multiplied by the Lagrange multiplier, which acts as a penalty for violating the restriction. The process to follow is: relaxed problem. For any fixed set of multipliers, solving the relaxed problem is usually easy. Quote generation. The solution to the relaxed problem provides a limit to the optimal value of the original problem, a lower limit for minimization, an upper limit for maximization. Lagrangian dual. To find the best possible bound, we solve a secondary optimization problem, the Lagrangian dual, which seeks to maximize the lower bound, or minimize the upper bound, by iteratively adjusting the multipliers. Updating multipliers. The subgradient method is often used to update multipliers, moving them in a direction that penalizes current constraint violations. It can also work with cutting planes. In 1993, Beasley developed the subgradient method R for linear problems, PL. For mixed, MIP, or mixed nonlinear, MIMP, problems, the method will not necessarily converge to a gap of 0% due to the integer variables. The reason is that marginal changes in Lagrange multiply result in different integer values and thus changes in the objective functions of the subproblems. To model Lagrangian relaxation, LR, two questions must be decided. First, what constraints to relax to define the subproblems, and second, the strategy for updating the Lagrange multipliers. The objective function, together with the local MIMP constraints, define the upper Lagrange bound problem. By relaxing these constraints, the problem can be separated into a subproblem for each cluster. There are several alternatives in the literature. Foss et al. Selected a heuristic based on the subgradient method described in Beasley, 1993. The procedure is iterative and generates multipliers in a systematic fashion from an initial set of multipliers. Upper and lower bounds on the solution must be calculated after each iteration. These bounds can also be used to quantify the quality of the solutions obtained. The upper bound will equal to the solution of a problem while the lower bound is usually found by some heuristics, that is equal to the original objective function. The alternative is to use cutting planes, which is High's preferred method. The problem of economic dispatch uses a monolithic model that is traditionally solved by large-scale optimization techniques. This problem can be solved in parallel, but it remains monolithic. Bender's decomposition is the most widely used and most recognized theory in solving DP and UC problems. To solve the problem, a master model and several subproblems are designed that establish an exchange of dual and primal variables. The master problem sends primal variables to the subproblems. Bender's theory works in the primal feasibility zone. Lagrangian relaxation is the alternative to Bender's theory and uses a similar architecture. To solve the problem, a master model and several subproblems are designed that establish an exchange of dual and primal variables. The master problem sends dual variables to the subproblems. Lagrangian relaxation theory works in the dual feasibility zone. However, Lagrangian relaxation is the basic theory of DP and UC in Industry 6.0. The problem of Lagrangian relaxation must be broken down into four problems. Master problem, in charge of coordinating the subproblems, and 3 subproblems, one for each entity of the system. To solve the problem, a conversation is established between the master problem and the subproblems. The coordinating problem sets values of the dual variables, marginal costs, and the subproblems return information based on the primal variables. LR worked in the non-feasible zone of the primal variables, and in the feasible zone of the dual problem. In this case, Lagrange theory indicates that there is only one Lagrange multiplier and, therefore, it must be equal in all subproblems. The convergence of the integrated problem is achieved when in 2 consecutive iterations, the value of the Lagrange multipliers remains constant. The image presents the use of Lagrangian relaxation to solve the smart grid problem. Each subproblem corresponds to a smart grid, and the master problem is equivalent to the smart grid control center. The relaxed restrictions on all smart grids are the demand for energy, and the generation of energy, and if applicable, it must balance purchases and/or sales with the utility linked to the smart grids. Marginal costs indicate the price of energy for each period. In Industry 4.0, since 2000, economic dispatch models begin to evolve towards a multi-problem mathematical model, which in high ends up becoming the artificial hypothalamus and net of supply models. During Industry 4.0, all the models that make up the artificial hypothalamus of the wholesale market in the electricity sector use a coordinating model, based on Bender's theory or on Lagrangian relaxation. Autonomous Lagrangian relaxation. Consensus algorithms. Autonomous Lagrangian relaxation theory. LR is about solving the monolithic problem using large-scale optimization methodologies. Although the solution process may be parallel, the problem remains integrated and requires a coordination problem. ALR is about using a consensus algorithm so that each problem is solved independently, and the solution is obtained through a consensus among the players participating in the game. The rules of consensus are based on the Lagrange theory. There is no monolithic problem, there are n independent problems. To determine optimality, the advanced metering infrastructure, AMI, of all electric systems must match. To do this, each electric system knows all the AMIs and moves towards the Lagrange multiplier solution. The electric systems will move autonomously, following logical rules that guarantee convergence, for example, moving towards the average of the Lagrange multipliers. For static processes, this consensus rule ensures that the problem will be optimal. Considering that LR is a primal non-feasible method, to use its results at any time, it is necessary to implement a mathematical problem that recovers the primal feasibility. In this case, it is a matter of recovering the feasibility of the demand in the generation equations. The feasibility recovery problem can be independent and reside in the AMI. To do this, it is necessary to implement an empirical rule of consensus based on optimization. The evolution of Lagrangean relaxation, LR, in Industry 6.0 has been named by High as autonomous Lagrangean relaxation, ALR. ALR is based the mathematical principles of Lagrange theory but is aimed at modeling living intelligent systems, which are autonomous and do not require coordination problems. On the other hand, its greatest strength is the modeling of systems in real time, based on intelligent sensors. ALR can also be called distributed Lagrangean relaxation, DLR. To differentiate itself from distributed Lagrangean relaxation, DLR, Lagrangean relaxation can be called centralized Lagrangean relaxation, CLR, since the model remains monolithic, and is solved in parallel using large-scale optimization technologies. ALR is based the mathematical principles of Lagrange theory but is aimed at modeling living intelligent systems, which are autonomous and do not require coordination problems. On the other hand, its greatest strength is the modeling of systems in real time, based on intelligent sensors. ALR is about using a consensus algorithm so that each problem is solved independently, and the solution is obtained through a consensus among the players participating in the game. The rules of consensus are based on the Lagrange theory. There is no monolithic problem, there are n independent problems. To determine optimality, the advanced metering infrastructure, AMI, of all electric systems must match. Today in the Industry 6.0, the artificial hypothalamus of the wholesale market in the electricity sector does not require a coordinating model. All the models can act autonomously and independently, and the optimal solution is achieved by means of consensus rules based on the mathematics of optimization proposed by Lagrange in the 1700s. High-power, autonomous optimization software for electric sector enterprises is an optimization decision support system oriented to agents acting in electricity systems, electricity wholesale markets, and smart grids. High-power integrated the following models. High-E electricity supply chain optimization supports decisions in the electricity supply chain, in terms of sectoral planning and business generation. High smart grids optimization supports the decisions of the various agents involved in the smart grids business. High natural gas supply chain optimization supports the decisions of the actors involved natural gas supply chain at the level of sectoral planning and business generation natural gas. According to the structure of modern electricity markets, the support of the business decision-making power generation should be seen from several points of view. Central agents, formed by the regulator, supervisor, planner, and system operator. Generators, agents that operate power plants. Distributors, utilities enterprises. Traders. Smart grids operators, and industrial companies. High L and high SGO cover all levels of the electricity systems. Electricity system and wholesale market optimization models. Hydro system physical modeling. High water corresponds to a general model that includes all kinds of hydraulic components, reservoirs, hydroelectric power plants, rivers, overflow channels, connection points and pumping stations, demands, like irrigation, aqueducts, environmental, industrial. Components can be freely linked to form any topology, like pumping storage systems. Hydroelectric power plants are modeled independently of reservoirs, so plant-reservoir connectivity must be established. The regulation capacity of the reservoir is simulated in detail, so such a simulation consistently represents the dispatch of the power plants, considering their ability to regulate the multi-annual, annual, hourly water resource. Electric system physical modeling. Electrical connectivity is carried out through a network of circuits and bars that integrates different types of installations, power plants, like hydroelectric, thermoelectric, coal, wind, solar, biomass, places of demand, like industrial, cities, regional interconnections and energy storages. High power includes the simulation and several types of renewable energy sources and energy storages. For each type of electrical asset, high power includes the exact equations for simulation. Natural gas system physical modeling. High gas describes the process of supply and demand of natural gas. From this point of view, its integration with the electricity system determines the economic equilibrium electricity-gas markets. The entities of the natural gas system are: node, connect the gas system installations; production fields; consumption zones, discriminated by sector, example, refineries, heavy industries, residential, vehicular, and commercial thermoelectric power plants; transport systems, pipelines, and multimodal transport systems using vehicles, pumping stations, compress the gas to transport it, and ports, receive and ship liquefied natural gas, LNG, and have gas storage capacity. Connectivity between the electricity and gas sectors occurs through the demand for natural gas for use in thermal plants, and the substitution of the demand that can occur between gas and electricity. Electricity system and wholesale market mathematical models make up a flexible decision support system that provides different types of services in an integral way. They can be classified into integrated dispatch of generation plants, optimization of generating agents, and predictive analytics of stochastic processes. Traditionally, the optimization models in the electricity sector consider individual modeling with exogenous coordination between models, based on multi-stage stochastic programming, and using large-scale optimization methodologies. The differences with the state-of-the-art modeling, provided by high power, are integrated holistic modeling, scientific risk modeling, multidimensional uncertainty, parallel optimization, and autonomous real-time distributed optimization. Three types of connectivity of the generation system and the transmission power grid are considered: ideal single node, ideal dispatch ignoring the transmission system; electric transmission network connectivity based on the detailed connectivity of the electricity transmission system using bars and circuits; operative areas connectivity, when the user does not have, or does not want to use, the detailed configuration of the electricity transmission grid. It is possible to use the connectivity based on operational area //app. Blaster online. com/speech low/ changelogs including limits on the transfers between areas. Interconnection electricity, gas integrates electricity network with natural gas network. Interconnection of electricity and water can be fully detailed, including travel times between nodes and transport restrictions in water resource conduction channels. The central model of high power is the standard representation of the electricity and gas supply chains. These equations give rise to variations of the model according to the techno-economic concepts that support a specific modeling. There are at least 4 types of economic models to represent the electricity and gas market: economic perfect dispatch, EED; economic regulated dispatch, ERD; Nash-Carnot equilibrium dispatch, NCD, and unit commitment, UC. The EED is the core model of high power, as its equations/constraints are used in multiple specific models that the agent requires to address decision support needs. EED and the UC models optimize the dispatch of generation infrastructure, minimizing the cost of operating the electricity system, which simulates a perfect electricity market. The differences between these two models are the detail of modeling. EDD is oriented to planning and UC to real dispatch. Economic regulated dispatch, delivery of plants that minimizes the cost of operation of the interconnected system and includes representatives aspects of the regulatory of the electricity market being simulated. It does not correspond to a model of economic equilibrium, however, It is an easy and fast way to represent regulatory considerations based on optimization models. Nash-Carnot equilibrium, dispatch of plants oriented to the simulation of competitive electricity markets with agents that can influence with their decisions on transactions occurring in the market. It can be used to, among others, project the dispatch of a competitive market, and study the exercise of dominant market power of agents. Four models are considered fundamental to support the strategic, tactical and operational decisions of an agent that operates generation plants. The diagram presents the design of an integrated set of mathematical models to support the decision-making of a generator agent. Electricity dispatch and financial analysis. Integration dispatch models with assets liabilities management, ALM, financial models including risk management, to perform analysis of the financial impact of decisions. The main applications are the valuation of income and expenses of investment projects, energy installations, and valuation of energy companies, and integrated optimization of investments by global energy companies, taking as a reference the regulatory laws of the different regions or countries. The financial modeling results individualize the operating income and expenses, and can include all types of legal accounts. Electricity supply chain design and risk management, associated with strategic planning decisions related to resilient design of supply chain, in relation to capacity of reservoir, transfers, power plants and other assets of an electrical system. It may include risk management and financial planning. Energy trading and risk management. Optimal decisions related to trade energy and coverage of financial risks based on standardized or no bilateral contracts. It corresponds to a set of mathematical models aimed at supporting the decisions of the different agents involved in energy trading in long-term market, spot market, and secondary markets. The result of a risk analysis is the definition of Pareto curves of risk versus expected revenue, based on which the decision-maker must define the risk position he wishes to assume, varying between risk-prone and risk-averse. Maintenance optimization is oriented policy-making preventive maintenance of multiple central generation plants and others electrical assets. It can be applied to all assets in a regional or national grid. High-power man can be implemented following the principles of PHM, prognostics health management, for industrial asset maintenance, integrating specific models of predictive analytics for asset components and prescriptive analytics to optimize the integrated operation of the asset network. High power has been used by ISO, in Peru, and Market Supervisor, in Colombia, for planning and decision-making purposes. High power includes some predictive analytics models. Spot price modeling. The prediction of spot prices of the energy market is fundamental for the decisions made by an agent that participates in that market, whether buyer or seller, generator, trader, or distributor of energy. This is because the decision maker requires that the model's results that produce spot prices be used in other mathematical prescriptive models. The mathematical models to be used depend on the planning period, short, medium or long term, and the type of market considering the dispatch of the plants, by mathematical model, or by market agents offers in a free market. In free markets the situation is complex since the law of price formation cannot always be explained based on mathematical rules, explicit, clear and universal, that may integrate a mathematical model. Synthetic generation renewable energy sources. For the generation of synthetic scenarios of climate variables, there are two requirements: short-term, hours, days, and medium/long-term, weeks, months. Specific short-term models must be built for each renewable source. For the medium and long-term, there are three alternatives to generate synthetic scenarios. Synthetic statistical model for the generation of climatic variables, firing Metallis type. Generate synthetic series of climatic variables based on the mixture of historical series. Generate synthetic series based on the historical series having the ENSO series, El Niño Southern Oscillation, as an instrumental variable. Projected short-term hydrological contributions using variations and enhancements of Kalman filter. Smart grids optimization models. The work of many researchers in the operation of the network of smart grid is the starting point for the mathematical modeling of the high-end Industry 6.0. This is due to the proliferation of smart grids and the need to coordinate these electrical systems, which today are called the Internet of Energy. In a real case, using an economic dispatch model such as Industry 4.0, as a monolithic model solved with large-scale optimization technologies, is practically impossible, since there are smart grid networks in which industrial and residential smart grids coexist, and energy flows in all directions and at all voltage levels. In the Industry 6.0, artificial brain does not require a system supervisor. Each smart grid acts as a living industrial system, with its own artificial brain, allowing the smart grid to act autonomously and independently. In a regulated environment, generation, transmission, and distribution are operated by a vertically integrated enterprise, usually a state-owned, which has a monopoly on the supply of electricity. Conversely, in a deregulated environment, different parts of the electricity grid are owned and operated by different actors, and electricity markets provide a platform that fosters competition among participants. As each smart grid is, it requires a specific decision support system that allows the operator to interact with the entire electrical system. HiSGO provides all the analytical elements necessary to configure the specific DSS that each case requires. HiSGO is composed of forecasting models and optimization models aimed at supporting the decision-making of electric agents, smart grids, optimization of the economic and technical aspects related to smart grids and electricity companies, demand response for buildings and/or housing, demand response, optimization of energy management in facilities, such as universities, shopping centers, office buildings, homes, urbanizations, and small towns. Industrial energy efficiency, optimization of energy management in heavy industries intensive in energy consumption. Forecast renewable energy sources. They correspond to predictive analytics models focused on the prediction in the specific sites where are located the generation plants. Forecast of demand energy. Demand projections per years, months, weeks, days, hours. HiSGO is integrated by the following optimization models. Economic dispatch of the smart grid, optimization of the management of electrical energy in small cities, factories, universities, shopping centers, office buildings, urbanizations. Smart grid unit commitment, optimization of the dispatch of the electrical load in real time, or in the short term. Smart grid configuration, optimizing the network topology. It considers voltage control, configuration of feeders, location or activation or reallocation of electrical assets, like transformers, capacitors, and phase balancing. Smart grid design, optimization of the design or redesign of smart grids with modern power technologies. ETRM, electricity trading and risk management, decisions to buy and or sell electricity, in a long, medium and short-term market, one day in advance or the day of dispatch. Industrial energy efficiency results of the integration of production processes, transformation of matter, with industrial energy services, energy transformation, aimed at the simultaneous optimization of both industrial production and energy conversion that is related to polluting emissions of gases and liquids, associated with increasingly demanding environmental control laws. The high-power and HiSGO models can be integrated with complex industrial process models, in which it is necessary to redesign the power supply system according to the new power technologies. This type of model includes the simulation of polluting processes, for example, combustion in furnaces, to determine the optimal mixture of fuels in accordance with environmental regulations. HiL and HiSGO integrate them models and information systems around a common data model, allowing models to be connected automatically through the database or through RAM memory, integrating them as an artificial hypothalamus for an electricity company of wide coverage. Hi invites you to learn about our current methodologies and compare them with those of our competitors. The Plexos model is developed by the Energy Paradigm and developed as capable of producing the following services: co-optimization, nodal and zonal analysis, renewables and ancillary markets, hydro optimization, gas planning, and multi-objective decision optimization. Plexos is touted as the energy decision and analytics platform for all systems. Since 1987, the Brazilian company PSR is a global provider of consulting services, computational modeling and energy innovation, and actively contributes to research and development of optimization and data analytics solutions. PSR is comprised of more than 130 experts in engineering, economics, mathematics, high-performance computing, information technology, business development and communications, who deliver technical and innovative solutions designed together with our clients. PSR consulting and innovation models and services are applied in more than 70 countries in the Americas, Europe, Asia-Pacific and Africa, in a multitude of varied contexts, size of systems, maturity of economic development and of the energy industry. PSR is an important company in the sector. High Power is proud to be competitive with PSR's suite of models, but it is more modern as it is based on the development of software supported by artificial intelligence. Remember, all science as it grows toward perfection becomes mathematical in its ideas. Alfred Whitehead. Thank you very much for your attention.